So lastly, I want to talk about how beam splitters and the formalisms that we've introduced to understand beam splitters and model beam splitters, how these can be used to model processes outside of just beam splitters. So one example is quantum frequency transduction, but there's other examples as well. But we're just going to look at this case of quantum frequency transduction. So quantum frequency transduction is very important in quantum networks for converting photons between different wavelengths of light. So a photon at a higher, or qubits, and also converting qubit interactions between different wavelengths of light or different energies. So different energies of light and different energies might be better suited for different tasks in the case of quantum networks. So it turns out that for red detuned transduction, the Hamiltonian that describes the process of red detuned transduction actually is the beam splitter Hamiltonian. And there's a lot of references that go through kind of why this is. I've included one on this slide in case you want to check it out. But basically, understanding that this red detuned transduction it follows a beam splitter Hamiltonian, we can now see that the beam splitter Hamiltonian is actually a very generalizable model. So in order to kind of benefit from knowing that basically that transduction follows the beam splitter Hamiltonian, one way we can use this is by, for instance, computing what the fidelity of a transduced qubit would be given some amount of input noise and given some finite efficiency of transduction. So we can consider that our efficiency of transduction, or say our probability that we would transduce this qubit, is equal to, say, eta. And we can also parameterize the noise that's entering into this transduction process as this term f, which will basically be equal to your average number of photons that are kind of in your environment that are going to interfere with this process. So you can find your quantum state for so there will in general be some quantum state for these thermal photons that are going to interfere with this process, but you don't have to explicitly know what the quantum state is of each of these thermal photons, because that might be a little bit difficult. So instead, you can find cross operators that will directly act on your qubit that you're going to transduce, and these cross operators will just describe this process of this Hamiltonian. And the way you can find these cross operators is by basically doing a partial trace over your environmental noise to basically kind of ignore these photons or average them out. So doing this, we can find an expression for what the fidelity of a transduced qubit would be, given some noise and given some finite efficiency. And one thing that's kind of interesting to see is if you take the special case of setting your environment to the temperature T equals 0, this means that we don't have any noise photons, basically. So you set your noise photons to 0. You can see what happens to your Krauss operators, and they will actually turn into amplitude dipping Krauss operators, which will show basically we don't have any noise, we just have some probability that we will transduce and some probability that we don't transduce.